my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Mr. Galileo was correct in his findings.
Gravity is synonymous with life. Our capacity to transcend gravity is a measure of society's success. And each technological breakthrough is a harbinger of hope for a brighter future. But just what is gravity? Science views gravity as one of several fundamental forces: electricity and magnetism. These strong and weak nuclear forces. And the weakest of all is gravity. Gravity is the odd one out on two counts. There is no accepted quantum model to explain gravity, and there is no push-button method of generating gravity. Yet Sir Isaac Newton published his equation for universal gravitation more than 300 years ago, long before the other fundamental forces were understood or even discovered. This suggests there is something fundamentally misconceived about our conventional view of gravity. This is Newton's equation for universal gravitation. It describes the force of gravitation between two celestial bodies. In simple terms, it says the bigger they are, the stronger the gravitation between them. And the further away they are from each other, the weaker the gravitation between them. Convention teaches us that gravity is inherent to matter, and that the two celestial bodies, M1 and M2, attract each other. However, Newton did not accept this. Writing to Cambridge University colleague Dr. Richard Bentley, Newton reveals something little said. You sometimes speak of gravity as essential and inherent to matter. Pray, do not ascribe that notion to me, for the cause of gravity is what I do not pretend to know, and would therefore take more time to consider of it. Newton also had something to say about the nature of gravitation beyond that which is found in his equations. From another letter to Bentley, he writes that gravity should be innate, inherent, and essential to matter, so that one body may act upon another at a distance through a vacuum, without the mediation of anything else, by and through which their action and force may be conveyed from one to another, is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. Newton makes it quite clear. He regarded our conventional view of gravity to be notional and an absurdity. Newton thought in terms of a hypothetical particle, which he called a fluxion. This dispelled the idea of outer space as a vacuum, and can also be used to explain how one celestial body appears to affect another without gravity being inherent to matter. It also provides a quantum mechanism for gravity, albeit an incipient one. But Newton did not go as far as to elaborate upon the fluxion. There are at least two reasons. Newton had adversaries who would have quickly taken a pejorative analysis of such an unsubstantiated view. We also know that Newton worked to very strict criteria. We are to admit no more causes of natural things than such as are both true and sufficient to explain their appearance. We are certainly not to relinquish the evidence of experiments for the sake of dreams and vain fictions. Nevertheless, Newton did use the fluxion concept. He used it to develop the mathematics needed to calculate the rate of flow for very small forces, such as gravitation. In doing so, he produced a branch of mathematics we today call calculus. But Newton did leave us enough information to induct for ourselves some of the fluxion's qualities. We know enough about Newton's physics to know that the fluxion would work in a simple, mechanistic way. Given the task of moving a ball with only a handful of sand, there is no other way but to throw the sand at the ball. Given enough force, the ball will move. This simple analysis reveals something remarkable. Newton's logic describes gravitation in terms of a force that pushes. This is in stark contrast to convention, which says gravitation attracts. Newton's equation treats gravitation as ostensibly instantaneous, but he knew this could not be taken literally, no more than a person can be in two places at the same time. This means the fluxion would have to move at tremendous speed, far faster than the speed of light. But at these speeds, the fluxion would have to pass straight through matter, virtually unimpeded. For this to happen, the fluxion would have to be very, very small indeed, far smaller than the smallest molecule or atom. It may necessarily be the smallest particle in existence. But at the same time, they must also create enough pressure to push the planets. That is, create gravitation. So matter must, in some way, attenuate some fluxions. We are not the first to give such consideration to Newton's fluxion. Nicolas Fatio de Duilier, a close colleague of Newton's, was the first to openly voice its implications. But it was left to his compatriot, Swiss physicist Georges-Louis Lesage, a contemporary writing shortly after Newton's death, to be the first to publish a pushing graviton hypothesis. Lesage's particle is called the ultra-mundane corpuscle, but it never caught on, even though this type of particle is today generally referred to as the graviton. In a post-Newtonian world where empiricism was the order of the day, Lesage was crucially unable to offer a supporting experiment. The ultra-mundane corpuscle was considered too ultra-mundane, just too out of this world. Yet, significantly, it is a quantum model, the very thing that has empowered today's technologists working with the other fundamental forces.